Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're tackling a practice problem set that covers electromagnetic radiation, wave-particle duality, quantum numbers, electron configuration, and periodic trends. Let's go ahead and get started with problem number 1. Problem number 1 says, which set ranks the various types of electromagnetic radiation from lowest to highest energy? In this problem, we're comparing 4 types of electromagnetic radiation: microwaves, infrared light, ultraviolet light, and X-rays. And we want to rank these 4 from lowest to highest energy. But before solving this specific question, it's useful to understand a systematic way to approach any variation of this type of problem. The first thing to know is the order of the electromagnetic spectrum. A helpful mnemonic to remember this order is red, Martians invaded Venus using X-ray guns. R is for radio waves, M is for microwaves, I is for infrared, V is for visible light, U is for ultraviolet light, X is for X-rays, and G is for gamma rays. From here, we need to recall that among all forms of electromagnetic radiation, gamma rays have the highest energy, and radio waves have the lowest energy. So as you move from radio waves to gamma rays, energy is going to increase. But what does that mean for frequency and wavelength? The relationship between these variables is explained by 2 key equations. The first equation tells us that energy is equal to Planck's constant multiplied by frequency. And the second equation tells us that the speed of light, which is a constant, is equal to wavelength multiplied by frequency. The first equation tells us that energy is directly proportional to frequency, meaning as energy increases, so does frequency, and as energy decreases, so does frequency. The second equation shows us that wavelength and frequency are inversely proportional, meaning longer wavelengths correspond to lower frequencies, and shorter wavelengths correspond to higher frequencies. This means that if energy is increasing as we go from radio waves to gamma rays, then frequency is also increasing and wavelength is decreasing. Now that we have this foundation, let's return to the original question. We need to rank microwaves, infrared light, ultraviolet light, and X-rays from lowest to highest energy. Looking at our spectrum, microwaves have the lowest energy among these, followed by infrared, followed by ultraviolet light, and then finally X-rays, which have the highest energy. This matches answer choice C. Problem 2 says, complete the sentence to make a true statement. As wavelength increases, frequency blink, and energy blink. We just talked about how wavelength and frequency are inversely proportional. So as wavelength increases, frequency is going to decrease. So in this first blink, we're going to put decreases. We also talked about the relationship between frequency and energy. If frequency is decreasing, then so is energy. So the second blink is also decreases. Let's read the full statement now. As wavelength increases, frequency decreases, and energy decreases. The correct answer for problem 2 is D. Problem 3 says, what is the energy of a photon with a wavelength of 6.63 nanometers? To solve this problem, we're going to be using the following equation. Energy is equal to Planck's constant multiplied by the speed of light divided by wavelength. If you're wondering where this equation comes from, it comes from the fact that we rearrange the speed of light equation to solve for frequency. This gives us that frequency is equal to the speed of light divided by wavelength. We take this definition of frequency and we replace the frequency term in our energy equation with it. And that gives us energy is equal to Planck's constant multiplied by the speed of light divided by wavelength. Now, H and C are both constants that we know. Planck's constant is equal to 6.626 times 10 to the minus 34 joules times second. The speed of light is approximately 3 times 10 to the 8 meters per second. And we're given wavelength, which is equal to 6.63 nanometers. The first thing you should notice is that the unit of length in wavelength and in the speed of light constant do not match. We want to make sure they match. So we need to convert one of these variables into units of meters. It's easiest to convert wavelength from nanometers to meters. And we can do that very easily because we know 1 nanometer is equal to 10 to the minus 9 meters. So we can rewrite wavelength as 6.63 times 10 to the minus 9 meters. With that conversion made, we can start plugging things into our equation. Energy is equal to Planck's constant, 6.626 times 10 to the minus 34 joules times second, multiplied by the speed of light, 3 times 10 to the 8 meters per second, and that's divided by wavelength, which is 6.63 times 10 to the minus 9 meters. Here, our seconds cancel, our meters cancel, and we're left with units of joules, which is exactly what we want because we're calculating energy. Now, you can plug this into a calculator and get an answer, but I'm also going to show you how you can make some slight approximations and do this calculation without the use of a calculator. What we notice is that in the denominator 6.63 and in the numerator 6.626, we can essentially approximate this to 6.63 and cancel those out. What we're left with is a bunch of these 10 to some exponents and a 3 in the numerator. We're going to go ahead and take out that 3 in the numerator, and let's deal with all of the exponents here. In the numerator, we have 10 to the negative 34 multiplied by 10 to the 8, and that's divided by 10 to the minus 9. To do the numerator first, when you're multiplying these together, you simply have to add their exponents. So 10 to the minus 34 multiplied by 10 to the 8 is just 10 to the minus 34 plus 8. And that's going to be equal to 10 to the minus 26. Now, 10 to the minus 26 is divided by 10 to the minus 9. How do we deal with division here? We simply subtract the numerator from the denominator. So 10 to the minus 26 minus negative 9. So this is equal to 10 to the minus 26 plus 9. And that's going to be equal to 10 to the minus 17. So our final answer is 3 multiplied by 10 to the minus 17 joules. The correct answer here is C. For my students, you're allowed to use a calculator, so you don't have to do it without the use of a calculator. But if we have other viewers watching here and they're not allowed to use a calculator, this is the way that you would approach this type of problem. Let's move on to problem 4. Problem 4 says, what is the wavelength in micrometers of a photon with a frequency of 1.5 times 10 to the minus 4 hertz? To solve this problem, we'll be using our speed of light equation. This equation tells us that the speed of light is equal to wavelength multiplied by frequency. We know the constant and we're given frequency. We want to solve for wavelength. So let's rearrange this equation to solve for the wavelength variable. Wavelength is equal to the speed of light divided by frequency. Let's plug in the values and solve. The speed of light is approximately 3 times 10 to the 8 meters per second. Frequency is equal to 1.5 times 10 to the negative 4 hertz. By the way, hertz is just equal to 1 over seconds. So our seconds units cancel out, And we're going to get our final answer in units of meters. Now you can plug this into a calculator, or you can do this by hand. To do it by hand, we'll first tackle these numbers. 3 divided by 1.5, that's equal to 2. And then we'll deal with the 10 to the exponent terms. What we have in the numerator is 10 to the 8, and what we have in the denominator is 10 to the negative 4. To solve for this, we need to subtract the exponents. So it's 10 to the 8 minus negative 4. And that's equal to 10 to the 8 plus 4, which is 12. So our answer is 2 times 10 to the 12 meters. We're not done though. We want this wavelength in units of micrometer. So we need to do a conversion. What is the conversion for meters to micrometers? 1 micrometer is equal to 10 to the minus 6 meters. So we'll take our answer, 2 times 10 to the 12 meters, and we're going to multiply this by our conversion factor. 1 micrometer is equal to 10 to the minus 6 meters. So now we have one more multiplication and division we have to carry out here. 2 times 10 to the 12 times 1 is just 2 times 10 to the 12. And then we have that divided by 10 to the minus 6. Our meters cancel out. Our final answer is going to have units of micrometers. To deal with the exponents here, it's going to be 10 to the 12 minus negative 6, which is equal to 10 to the 18. So our final answer is 2 times 10 to the 18 micrometers, which matches with answer choice D. Problem 5 says, which statement below is false? Let's read each answer choice and work through it. Statement A says that electrons are excited by visible light. This is a true statement because visible light has enough energy to promote electrons to higher energy levels in atoms and molecules. Statement B states that X-rays excite core electrons. This is also true. X-rays have very high energy and they are capable of removing or exciting electrons from the inner atomic orbitals. Statement C says microwaves excite the spin of a nucleus. This statement is false. While microwaves can interact with molecules, they primarily cause rotational transitions rather than nuclear spin excitations. It's actually radio waves that are going to interact with nuclear spins. So C is the false statement, and it is the correct answer for problem 5. But let's read statement D as well. Statement D says molecular vibrations can be caused by exposure to infrared light. This is correct because infrared radiation has the right energy to excite vibrational modes in molecules, which is why infrared spectroscopy is widely used to study molecular structures. So again, the correct answer for problem 5 is C. Problem 6 says, what will occur when a photon with a wavelength of 331.3 nanometers strikes a potassium surface that has a work function of 4 times 10 to the minus 19 joules? The key idea here is the photoelectric effect. The photoelectric effect states that an electron is ejected from a metal surface if the photon's energy is greater than the work function of the metal. Any excess energy after that is going to be converted into kinetic energy of the ejected electron. And we can calculate this as the difference of the photon's energy and the work function. To find the energy of the photon, we are going to use this equation. Energy is equal to Planck's constant multiplied by the speed of light divided by wavelength. And we chose this particular equation because we know these two constants and we're given the wavelength. Now, Planck's constant is equal to 6.626 times 10 to the minus 34 joules times second. The speed of light is equal to 3 times 10 to the 8 meters per second. And the wavelength is 331.3 nanometers. Now we want to go ahead and convert that to meters so all of the units properly cancel out. This is going to be equal to 331.3 times 10 to the minus 9 meters. You can plug this into a calculator or you can do this by hand. To do this by hand, the first thing we want to do is rewrite the denominator. I'm going to go ahead and move this decimal place 2 places to the left. When I do that, I have to add 2 to this exponent. So that means our denominator is now 3.313 times 10 to the minus 7 meters. And the reason I did this is because I'm going to approximate this value to 3 and have these 3's in the numerator and denominator cancel out. The other thing I'm going to do is I'm just going to approximate this to 6. I'm going to approximate it to 6 and then I'm going to take it out of the numerator and write it right here. If I do that, all I am left with is these 10 values raised to some exponent. We have 10 to the minus 34 multiplied by 10 to the 8 in the numerator. And then we have 10 to the negative 7 in the denominator. The exponents in the numerator add up, and then we subtract that from the denominator. So it is going to be negative 34 plus 8 minus negative 7. This is essentially negative 34 plus 8 plus 7, and this gives us a value of negative 19. So the energy of our photon is approximately 6 times 10 to the minus 19 joules. Let's compare this value, the energy of the photon, to the work function. We notice that the energy of the photon is in fact greater than the work function. That means that electrons are in fact ejected. We know they're ejected, but we still don't know what their kinetic energy is. That's the second part of this question. To determine the kinetic energy of the ejected electrons, we're going to have to use this equation. The kinetic energy of the ejected electron is going to be the difference between the photon's energy and the work function of the metal. To do this subtraction, we're going to go ahead and take out this common factor, 10 to the minus 19 out, and we're left with 6 minus 4 joules. This is going to be equal to 2 times 10 to the minus 19 joules. So we have an ejected electron that has a kinetic energy of 2 times 10 to the minus 19 joules. The correct answer for problem 6 is B. Let's move on to problem 7. Problem 7 says light of 514 nanometers is shown onto a metal surface in a vacuum. A detector does not show the presence of any ejected electrons. What change could possibly lead to the ejection of electrons? Let's read through every option and see which one is true. Ultimately, for an electron to be ejected, the photon's energy needs to be greater than the work function of the metal. At this wavelength, the energy of the photon does not exceed the metal's work function. What change could we make that would lead to the ejection of electrons? Let's read option A. Option A says that the intensity of the light could be increased, and that would lead to the ejection of electrons. This is not correct. Increasing intensity simply means that we're sending in more photons to hit the metal surface. But these photons are still going to carry the same energy, meaning they're not going to cause any electrons to be ejected. This is not the change we want to make to eject electrons. Answer choice B says, the metal is exchanged for a metal with a higher work function. This is also incorrect. Using a metal with a higher work function would actually make it harder for electrons to be ejected, since the threshold energy required would increase. If electrons aren't being ejected now, increasing the work function is most definitely not going to help. Answer choice C says that the frequency of the light is decreased. This answer choice is incorrect. If we decrease the frequency of light, that means we're going to be decreasing the energy of the photon, since energy and frequency are directly related. A photon with lower energy is not going to allow an electron to be ejected. That's not the change we want to make. So C is incorrect. D says the wavelength of the light is decreased. This is the correct answer. If we decrease the wavelength of light, then we're going to increase the energy. And that's because wavelength and energy are inversely related through this equation here. So decreasing the wavelength will increase the energy of the photon. And if we increase the energy of the photon, now we have the potential of surpassing the metal's work function and ejecting an electron. So D is the correct answer. Problem 8 says, iron has a work function of 4.5 electron volts. A single 2.25 electron volt photon strikes the iron surface. What is the expected outcome? The key principle from the photoelectric effect states that if the energy of the photon exceeds the work function, then an electron will be ejected. And any excess energy is going to be converted into kinetic energy of that ejected electron. In this particular case, the work function is 4.5 electron volts, and the energy of the photon is 2.25 electron volts. The energy of the photon is actually less than the work function. So that means the photon's energy is insufficient to overcome the work function, and no electrons will be ejected from the metal surface. The correct answer here is A. Problem 9 says, what is the Rydberg equation used to calculate? This equation, it allows us to determine the frequency of light emitted or absorbed when an electron transitions between energy levels in a hydrogen atom. Keeping that in mind, let's work through the options. A says the frequency of a photon emitted or absorbed by a hydrogen atom. This is correct because the Rydberg equation directly calculates the frequency of radiation associated with electron transitions in hydrogen. This is the correct answer, but we're going to read B, C, and D anyway. B says the frequency of a photon required to eject an electron from a hydrogen atom. Incorrect, because this relates to the photoelectric effect, which depends on the work function and not the Rydberg equation. So B is incorrect. C says the distance between quantum levels of a Bohr model atom. This is incorrect because the Rydberg equation does not directly provide spatial distances, only the frequency or energy of transitions. So C is incorrect. D says the speed of electron transitions between energy levels in Bohr model atom. This statement is incorrect because the equation does not describe the time or speed of transitions, only the energy or frequency of the emitted or absorbed photons. With that being said, the correct answer for problem 9 is A. Problem 10 says, which transition would lead to emission of a photon with the longest wavelength? When you're solving this problem, keep two things in mind. The first thing is that wavelength and energy are inversely related. So the longest wavelength corresponds to the smallest energy change. The second thing is that this problem specifies emission, which means we are looking for a transition where an electron moves from a higher energy level to a lower energy level. This allows us to immediately cross out A and B because they are both absorption processes. We're left with C and D. In C, we're moving from n equals 3 to n equals 1. And in D, we're moving from n equals 3 to n equals 2. The correct answer is going to be D. This is an emission process with the smallest energy change given the options. Since wavelength is inversely proportional to energy, a smaller energy difference results in a longer wavelength photon. And that is why D is the correct answer. Problem 11 says, what is the energy of a photon absorbed in the transition of an electron from n equals 1 to n equals 2? The Rydberg equation is going to help us calculate the frequency or energy of the photon that's involved in this transition. The equation for this is as follows. The energy is equal to the Rydberg constant multiplied by 1 divided by the lower energy level squared minus 1 over the higher energy level squared. Our lower energy level is 1 and our higher energy level is 2. Looking at the answer choices, we notice that R, the Rydberg constant, is not multiplied out. So we're not going to multiply the Rydberg constant with what's in the parentheses. Instead, we're going to solve for what's inside these parentheses and multiply it by R, keeping R as is. So let's work on that part. The lower energy level is 1, so this is 1 over 1 squared minus 1 over 2 squared. This is equal to 1 minus 1 over 4, and that is equal to 3/4 or 0.75. And let's not forget R. So what is the energy of a photon absorbed in the transition of an electron from n equals 1 to n equals 2? In a hydrogen atom, that's going to be equal to 0.75 R, or answer choice D. Problem 12 says, what properties are described by the de Broglie equation? A says the wave-particle duality of light. B says the wave-particle duality of matter. C says the wavelength of photons with mass. And D says the speed of electromagnetic radiation. Now, the de Broglie equation, it describes the wave-particle duality of matter, and it demonstrates that particles with mass, such as electrons, can exhibit wave-like behavior. And this idea was fundamental in the development of quantum mechanics because it showed that not only does light exhibit both wave and particle properties, but matter itself also has an associated wavelength when in motion. So the correct answer here is going to be B. The de Broglie equation shows the wave-particle duality of matter. Problem 13 says, complete the sentence to make a true statement. According to the de Broglie equation, wavelength increases as mass blank and speed blank. The de Broglie equation says that wavelength is equal to Planck's constant divided by mass times velocity. This equation shows that the wavelength of a particle is inversely proportional to both its mass and its velocity. So this means that as mass increases, the wavelength decreases. As velocity increases, the wavelength also decreases, and vice versa. If the mass decreases, then the wavelength decreases. And if the velocity decreases, then the wavelength also decreases. So to fill in the blank, according to the de Broglie equation, wavelength increases as mass decreases and as speed decreases. So the correct answer here is D. Problem 14 says electrons have a diameter of 1 × 10⁻14 meters and a mass of 9.1 × 10⁻31 kilograms. At what speed does the wavelength of an electron exceed the diameter of an electron? We are given that the diameter of an electron is 1 times 10 to the negative 14 meters, meaning that for the electron's wavelength to exceed this value, we set that the wavelength is greater than or equal to this value. Next, we want to take our de Broglie equation and we want to rearrange to solve for speed. So we want to isolate this variable v. V is equal to Planck's constant divided by mass times the wavelength. We have all of these variables and values, so we're just going to go ahead and plug them in. Planck's constant is 6.626 times 10 to the negative 34 joules times second. The mass of the electron is 9.1 times 10 to the minus 31 kilograms. And that's multiplied by the wavelength, which we're going to use 1 times 10 to the negative 14 meters for. Now, we can plug this into a calculator and get an answer. We can also work through this by hand. So I'm going to show you how to do that. Step 1 is we're going to simplify the denominator since we're multiplying two values there. So we are dealing with 9.1 times 10 to the minus 31 multiplied by 1 times 10 to the negative 14. We'll deal with the number values first. 9.1 times 1 is just 9.1. Now we'll deal with the exponents. We have 10 to the negative 31 multiplied by 10 to the negative 14. When we're multiplying these to get the answer, we simply have to add the exponents. So it's going to be equal to 10 to the minus 31 plus negative 14. And this is equal to 10 to the negative 45. Our numerator is 9.1 times 10 to the negative 45. Let's rewrite our expression, 6.626 times 10 to the negative 34 in the numerator, and 9.1 times 10 to the negative 45 in the denominator. Let's divide these values first. We have 6.6 divided by 9.1. I'm going to approximate this to 6, and I'm going to approximate this to 9. 6 divided by 9 is equal to 2 divided by 3, which is approximately 0.6666, and so on and so forth. We can also just go ahead and approximate this value to 0.7. That's an easy value to deal with. The second part we have to deal with is these exponents. They're being divided, which means we have to subtract the exponents. So 10 to the minus 34 minus negative 45. This is just negative 34 plus 45, and that's equal to 10 to the 11. So our speed is equal to 0.7 times 10 to the 11. And the units that are associated with this is meters per second. We're going to go ahead and do one more change to this value. We're going to go ahead and move this decimal over to the right one place. And now we have 7 times 10 to the 11 minus 1. When we move the decimal to the right, we subtract from the exponent. And when we move the decimal to the left, we add to the exponent. So here we move the decimal to the right, we have to subtract from the exponent. We only move the decimal place one place to the right, so we only have to subtract 1 from the exponent. This gives us 7 times 10 to the 10th power. And this is going to be meters per second. The answer choice that's closest to this value is going to be answer choice C. Again, for my students, you could have just plugged this into your calculator and gotten an answer since I allow calculators on the exam. But for people who are watching this that might have to do all of these calculations by hand, that's the trick to it. Let's move on to problem 15. Problem 15 says, according to de Broglie, which particle is expected to have the largest frequency if all of the particles are traveling at the same velocity? To answer this problem, we need to take a look at our de Broglie equation. Our de Broglie equation says that wavelength is equal to Planck's constant multiplied by mass times velocity. Since all of the particles, the electron, proton, atom, and molecule, are all traveling at the same velocity. The only variable that affects wavelength is going to be mass. From the equation, as mass increases, wavelength decreases because they are inversely proportional. Since wavelength and frequency are also inversely related through this equation, we can conclude that as mass increases, frequency increases. And among the options, a molecule has the greatest mass. Because a larger mass leads to a smaller wavelength and higher frequency, the correct answer for problem 15 is D. Problem 16 says, at what speed, meters per second, must a 20-gram tennis ball travel to have a de Broglie wavelength that is equal to that of a photon of green light, which has a wavelength of approximately 331.3 nanometers? For this problem, we want to start by writing our de Broglie equation, and then we want to rearrange it to solve for speed. So wavelength is equal to Planck's constant divided by mass times velocity. We want to isolate velocity here. By rearranging the equation, we get that velocity is equal to Planck's constant divided by mass times wavelength. We have all of these values, so we can just substitute them in. Planck's constant is 6.626 times 10 to the negative 34 joules times second. The mass is 20 grams, but we want to convert that to kilograms. So that's going to be 2 times 10 to the negative 2 kilograms. And that's multiplied by wavelength. We're given the wavelength in nanometers. We want it in meters. 331.3 nanometers is equal to 331.3 times 10 to the negative 9 meters. There's one more change I want to make here. I actually want to move this decimal place 2 places to the left. When I move the decimal places 2 places to the left, I need to add +2 to the exponent. So this is now written as 3.313 times 10 to the negative 7 meters. We're going to put that in our denominator. Now, we can plug this into a calculator and get an answer. If we want to do it by hand, the first thing we want to focus on is the denominator, since we have 2 things being multiplied in the denominator. We have 2 times 10 to the negative 2 multiplied by 3.313 times 10 to the negative 7. First, we'll multiply 2 and 3.313. That gives us 6.626. And then we'll deal with the exponents here. We're multiplying these out, so really we're going to be adding the exponents. When we add the exponents, we get negative 2 plus negative 7, and that's equal to negative 9. So the denominator is now 6.626 times 10 to the negative 9. Let's rewrite it. We have our numerator, which we haven't touched, 6.626 times 10 to the negative 34 joules times second. And now we have in our denominator 6.626 times 10 to the negative 9 kilogram times meters. What you notice is this is the same in the numerator and the denominator, so they cancel out. And all we're left with is 10 to the negative 34 divided by 10 to the negative 9. When you're dividing these, the rule is to subtract the exponents. 10 to the negative 34 minus negative 9. And this is going to be equal to 10 to the negative 25. Since these canceled out, this is just 1 times 10 to the negative 25. Our units here are meters per second for speed. And that best matches answer choice C. So 16 is C. Problem 17 says the shape of an atomic orbital is described by blank. Is it the principal quantum number, N? Is it the angular momentum quantum number, L? Is it the magnetic quantum number, ML? Or the magnetic spin quantum number, MS? The shape of an atomic orbital is defined by the angular momentum quantum number L, which defines the orbital subshell type and overall geometric structure. The possible values of L correspond to different shapes. So when L is equal to 0, we have our S subshell, which is spherical. When L is equal to 1, we have our P subshell, and they have a dumbbell shape. When L is equal to 2, we have our D subshell, and they have clover leaf-like structures. And when L is equal to 3, we have our F subshell. They have much more complex, multi-lobed structures. So the correct answer here is B. 18 says, which quantum number can have a value of 6? Is it the principal quantum number, the angular momentum quantum number, the magnetic quantum number, or the magnetic spin quantum number? The quantum number that can have a value of 6 is going to be the principal quantum number, which determines the energy level and size of an atomic orbital. The principal quantum number can take on any positive integer value, n equals 1, 2, 3, 4, 5, and 6. So n equals 6 is a valid value. The other quantum numbers have more restricted ranges. So the correct answer to 18 is A. Problem 19 says, what does an orbital describe? A says the probable area to locate an electron. B says the shape of an electron's path. C says the spin of an electron, and D says the path an electron orbits. An orbital, it describes the probable region in which an electron is likely to be found around the nucleus. So unlike the outdated Bohr model, which depicted electrons following these fixed circular orbits, quantum mechanics defines orbitals as three-dimensional probability distributions where electrons exist with a certain likelihood. So the correct answer for 19 is A. 20 says, how many electrons can have the quantum numbers n equals 3, L equals 1, ML equals -1, and MS equals -1/2? In this problem, we are provided with a value for all 4 quantum numbers. As we discussed in lecture, a set of 4 quantum numbers uniquely describes just one electron. So no 2 electrons in an atom can have the same exact set of 4 quantum numbers. This is stated in the Pauli exclusion principle. Therefore, the correct answer here is A. Only 1 electron can have this set of quantum numbers. Problem 21 says, how many electrons can have the quantum numbers n equals 4, L equals 3? So notice in this problem, we're only given the principal quantum number, which tells us that the electrons are in the 4th energy shell, and we're given the angular momentum quantum number, L equals 3. And that specifies that we are dealing with the F subshell. Within the F subshell, the magnetic quantum number can take on any values ranging from -3 to +3. And that is going to give us a total of 7 ml values. That number 7 corresponds to the possible orbitals you can find in the F subshell. So these 7 ml values tell us there are 7 orbitals in the F subshell. Each orbital can hold 2 electrons, one with a spin up and one with a spin down. And so 7 times 2 gives us a total of 14. 14 electrons can have the principal quantum number n equals 4 and the angular momentum quantum number L equals 3. So the answer is D. 22 says, what is wrong with the following set of quantum numbers? N equals 3, L equals 0, ML equals -1, and MS equals -1/2. So let's analyze each of these quantum numbers and see if they follow their respective rules. N is equal to 3. That is a very valid number for the principal quantum number. It represents the energy level of the electron, and n equals 3 is a positive integer value, which is the only restriction on the principal quantum number. Then the angular momentum quantum number L. This defines the type of subshell, and it has to be within a range. It has to be between 0 to n minus 1. L here is equal to 0. That is a completely valid angular momentum quantum number. Then, based off of the L value, ML can take on any number between negative L to positive L. Since L here is equal to 0, ML can only be equal to 0. But in this set of quantum numbers, ML is negative 1. That is incorrect. So we're looking for an answer choice that signals that the ML value is incorrect. And that's going to be answer choice B. There is only one orientation, 0, for the angular momentum quantum number L equals 0. Problem 23 says, which of the following sets of quantum numbers is not allowed? Let's work through each option. Answer choice A says n is equal to 2. This is a valid principal quantum number. L is equal to 1. This is also correct because when n is equal to a value like 2, L can be any value from 0 to n minus 1. So L can be 0 or 1. Here it's 1, and that's completely correct. Since L is equal to 1, ML can be any value between negative L to positive L. So an ML value of 1 is correct. And then our MS is negative 1/2. This follows all the rules for quantum numbers. Answer choice B says n is equal to 4, L is equal to 2, ML is equal to negative 2, and MS is positive 1/2. This is another set of valid quantum numbers that follows the rules. C says n is equal to 1, L is equal to 0, ML is equal to 0, and MS is negative 1/2. Again, a valid set of quantum numbers that follows our rules. Finally, we have D. D says n is equal to 5, L is equal to 5. That's where we see our first mistake. All right, this is where the mistake has occurred. When n is a value like 5, L can only be a value from 0 to n minus 1. L cannot be equal to n. So D is not a valid set of quantum numbers. It is not allowed. 24 says, how many electrons does the following ion contain? P3+. P is phosphorus. So the first thing we need to consider is the number of protons in a neutral phosphorus atom. If we take a look at the periodic table, phosphorus is right here. It has an atomic number of 15, meaning that a neutral phosphorus has 15 protons and 15 electrons. When phosphorus loses 3 electrons, it becomes phosphorus with a 3+ charge. So that +3 charge indicates that the atom has lost 3 electrons. So to find the number of remaining electrons, we just have to take our original 15 electrons in our neutral phosphorus and subtract 3 from there. And that gives us a total of 12 electrons. So P3+ has 12 electrons. Problem 25 says, how many of each type of subatomic particles does a Fe ion contain? So it wants us to figure out how many protons, neutrons, and electrons a fluoride ion has. To determine that, we need to start with neutral fluorine. Going back to our periodic table, fluorine is right here. It has an atomic number of 9, which means it has 9 protons. For a neutral fluorine, it also means that it has 9 electrons. However, this is a fluoride ion. It's fluorine with a -1 charge, so fluorine has gained an electron. And that means that it has 10 electrons instead. The number of protons, however, doesn't change. Now, the last thing we need to determine is how many neutrons fluorine has, how much neutrons F-1 has. This requires us to go back to our periodic table and get the mass number. The mass number for fluorine is approximately 19. If we have 9 protons and the atomic and the mass number is 19, we can just go ahead and take 19 and subtract 9, and that gives us the total number of neutrons. So F-1, or the fluoride ion, has 9 protons, 10 electrons, and 10 neutrons. The correct answer is A. 26 says, all alkali metals are blank. A says in the S block, B says are transition metals, C says contain d orbital electrons, and D says in the same period. So the alkali metals are group 1 elements. So they are definitely not in the same period. They're in the same group, and they are including hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. So all of these elements are classified as alkali metals. And these elements all have a single valence electron in an s orbital. So that makes them part of the s block in the periodic table. That means that the correct answer for 26 is A. They are not transition metals. You do not find them in this area of the periodic table where all of the transition metals lie. And they are not they don't contain any d orbital electrons, and they are not in the same period. They are in the same group. 27 says, chlorine is expected to have properties most similar to which other element? Let's locate chlorine on the periodic table. Chlorine is right here. Now, an important fact to keep in mind is that elements within the same group share similar chemical and physical properties because they have the same number of valence electrons. Halogens all have 7 valence electrons, and they readily gain 1 electron to achieve a stable noble gas configuration. So any element in the halogen group is going to have similar properties to chlorine. And the only answer that fits that criteria is iodine. Iodine is also found in the halogen group, and it's going to have properties that are most similar to chlorine. 27 is C. 28 says, select the true statement about the quantum mechanical model of an atom. A says orbitals describe a specific path the electrons travel. B says orbitals are maps showing the probable location of an electron. C says the farther the orbital is from the nucleus, the lower its energy. And D says the speed of an electron moves at is directly related to the wavelength of light absorbed or emitted. The correct statement about the quantum mechanical model of the atom is going to be B. Orbitals are maps that show the probable location of an electron. The quantum mechanical model, it describes electrons as existing in regions of probability called orbitals. And these orbitals are mathematical probability distributions that indicate where an electron is most likely to be found at any given time, rather than a specific path it follows. So 28 is B. All of the other statements are incorrect. A is incorrect because it describes the Bohr model, which assumes electrons travel in well-defined orbits around the nucleus, and that's incorrect. C is not the correct answer because higher energy orbitals are farther from the nucleus, not lower energy ones. So in quantum mechanics, electrons in orbitals with higher principal quantum numbers are generally found at greater distances from the nucleus, and they possess higher energy, meaning they are less tightly bound. So that's why A and C are incorrect. D is incorrect because the speed at which an electron moves is not directly related to the wavelength of light absorbed or emitted. Let's move on to 29. 29 says select the following statements about orbitals that are false. A says there are 4 subshells described by the angular momentum quantum number L. B says an electron in a 2p orbital spends more time close to the nucleus than an electron in a 2s orbital. C says a magnetic quantum number of 1 can describe the orientation of a p or a d orbital. And D says an electron moving from an orbital far from the nucleus to an orbital near the nucleus is called emission. The false statement here is going to be B. Statement B is false because on average, an electron in a 2s orbital spends more time near the nucleus than an electron in a 2p orbital. The other statements are all true. A says that there are 4 subshells described by the angular momentum quantum number. This is true. L equals 0 refers to the S subshell. L equals 1 refers to the P subshell. L equals 2 refers to the D subshell. And L equals 3 refers to the F subshell. And each of these subshells correspond to a different type of orbital shell. Option C is also a true statement because a magnetic quantum number of 1 can describe the orientation of a p orbital in 3-dimensional space. The possible values of ml for a p orbital are -1, 0, and +1, and they correspond to the 3 different orientations of p orbitals, px, py, and pz. Finally, D is also a true statement because emission occurs when an electron transitions from a higher energy orbital to a lower energy orbital, releasing energy in the form of a photon. Let's move on to problem 30. Problem 30 says which transition would lead to emission with the highest frequency? A says 1s to 2s, B says 3s to 2s, C says 1s to 2p, and D says 3s to 1s. Now, the first thing I want to point out is that this problem is asking which transition would lead to emission with the highest frequency. Emission occurs when an electron moves from a higher energy level to a lower energy level, and it releases energy in the form of a photon. The energy of that emitted photon is determined by the difference in energy between the 2 levels. So with that in mind, we can immediately cancel out A and C because they both describe an absorption process. What we're left with is B and D. And in this case, the largest energy difference is going to occur in the 3s to 1s transition because it involves an electron dropping from a much higher energy level, n equals 3, directly to the lowest energy level, n equals 1. And according to the equation, energy is equal to Planck's constant multiplied by frequency. A larger energy difference corresponds to a higher frequency photon. So 30 is D. 31 says a hydrogen atom emits light at 432 nanometers when an electron moves from n equals 5 to n equals 2. What wavelength in nanometers of light is observed when an electron moves from n equals 3 to n equals 2? Now, you can approach this problem logically, or you can calculate it using the Rydberg equation. The former is obviously easier. So this question, it refers to the Balmer series because we're going from a higher energy level back down to n equals 2. The given information states that the n equals 5 to n equals 2 transition emits light with a wavelength of 432 nanometers. And that means it has a certain amount of energy. Energy and wavelength, they're inversely related, and we can tell through this equation right here. As energy increases, wavelength decreases, and vice versa. So a transition involving a smaller energy difference, like n equals 3 to n equals 2, that's going to produce a longer wavelength, and it's going to be a smaller energy difference between those levels. So we're looking for an answer in our options that is a longer wavelength than 432 nanometers, and the only option that meets this criteria is A, 656 nanometers. 32 says, which would be expected to have the highest third ionization energy? Ionization energy is the energy required to remove an electron from an atom or ion, and it generally increases as successive electrons are removed. The first ionization energy, this refers to the removal of the outermost electron. Then the second ionization energy involves removing the next electron, and so on and so forth. When we talked about multiple ionization energies, we really focused on group 1 and 2 in class. Group 1 elements, the alkali metals, they have one valence electron. So their first ionization energy refers to the removal of that single valence electron. Once that single valence electron is removed, then the elements have a noble gas-like configuration. So attempting to remove a second electron from group 1 requires significantly more energy. For group 2, they have two valence electrons. So the elements in the alkaline earth metals, they have two valence electrons. So ionization energy 1 refers to the energy required to remove that first valence electron. And then the ionization energy 2 refers to the energy required to remove that second valence electron. Once those two valence electrons are removed, the group 2 elements achieve noble gas-like configuration. And that means attempting to remove a third electron after that requires a significant amount of energy. So for group 1 elements, the second ionization energy is extremely large. And for group 2 elements, that third ionization energy is extremely large. Our problem says which would be expected to have the highest third ionization energy. We're looking for an answer choice where the element is in group 2. And the only one that meets that criteria is magnesium. Magnesium has two valence electrons in the 3s subshell. Its first and second ionization energies correspond to the removal of these valence electrons, and they're relatively low compared to the third ionization energy. After losing two electrons, magnesium forms magnesium 2+, which has the electron configuration of neon, a noble gas. So removing an additional electron after that means disrupting this highly stable, fully filled inner shell. And that's going to require significantly more energy. And that's due to the strong electrostatic attraction between the nucleus and the remaining core electrons. So 32 is C. 34 says rank the following in order of decreasing ionic size. Ionic radius refers to the size of an ion, and it's influenced by both the number of the electrons and the nuclear charge. When the ions have the same number of electrons, though, then we're dealing with an isoelectronic species, and the primary factor affecting their size is the number of protons in the nucleus. For the same number of electrons, a greater number of protons results in greater nuclear charge that pulls electrons closer to the nucleus and results in a smaller ionic radius. Now, in this problem, we're given these four ions. We have S2 minus, Cl minus 1, potassium plus 1, and calcium 2 plus. They all have exactly the same number of electrons, 18 electrons. What's different between them is actually the number of protons. Sulfur has 16 protons. Chlorine has 17. Potassium has 19. And calcium has 20. With this increase in protons, the more protons there are for the same number of electrons, the greater the nuclear charge, which means this results in a smaller ion. In other words, sulfur, with its 18 electrons and 16 protons, is going to have the lowest nuclear charge among these isoelectronic species. And the reduced attraction between the nucleus and the 18 electrons allows the electron cloud to expand. So it's going to make sulfur here, sulfur 2-, the largest ion in the set. Then following that, the next largest is going to be chlorine with its 17 protons. Following that is potassium +1, and the largest is going to be calcium with its 18 electrons and 20 protons. So the answer in decreasing ionic size should be sulfur 2-, chlorine -1, potassium plus, and then calcium 2+. That is answer choice D. Problem 34 says, place the following ions in order of decreasing size. Here we again see an example of an isoelectronic series where different ions have the same number of electrons, but they differ in how many protons they have, and that affects their size. We have tellurium 2-, iodine -1, and then cesium +1. Each of these ions have 54 electrons, but they have different number of protons. Tellurium has 52 protons. Iodine has 53 protons, and cesium has 55 protons. The protons are going to pull the electrons inward. Since protons pull electrons inward, a higher proton count results in a smaller ion. So cesium, with its 54 electrons and 55 protons, is going to have the smallest radius, while tellurium, with its 54 electrons and 52 protons, is going to have the largest. Iodine falls somewhere in the middle. So the ordering for this series in decreasing ionic size is tellurium, iodine, then cesium. So B is the correct answer. 35 says, which of the following has the smallest first ionization energy? Lithium, potassium, fluorine, or sulfur? As a reminder, ionization energy refers to the energy required to remove an electron from a neutral atom in the gas phase. Looking at our periodic table, ionization energy generally increases across a period from left to right, and it decreases going down a group from top to bottom. This trend is due to increasing nuclear charge across a period, which pulls electrons closer, and increasing atomic size down a group, which weakens the hold on the outer electrons. Now, the 4 elements that we have as part of our answer choices are lithium, potassium, sulfur, and fluorine. So once again, ionization energy increases from left to right. Our goal is to figure out the smallest ionization energy. So that means that we probably should be looking somewhere around here, and we can eliminate fluorine and sulfur since ionization energy increases across a period. Now we're left with lithium and potassium. What is the trend regarding ionization energy going down a group? Well, it decreases. So that means among the given options, potassium has the smallest first ionization energy, and that is answer choice B. So 35 is B. 36 says, place the atoms in order of increasing size. Let's go back to our periodic table and let's recall what our trend for atomic radius is. Atomic radius is going to decrease across a period, and then it's going to increase going down a group. So if we are looking at placing chlorine, bromine, and fluorine in order of increasing size, let's figure out where they are on the periodic table. Here's fluorine, chlorine, and bromine. Notice they're in the same group. This is the halogen group. Going down a group, atomic radius increases. So bromine is going to have the largest radius. Then following that is going to be chlorine. And then finally, the smallest is fluorine. Looking at our answer choices, this is going to be answer choice D. Fluorine, chlorine, and bromine. 37 says, write the full electron configuration for the fluoride ion. The first step to solving this problem is writing the electron configuration for a neutral fluorine atom. Going back to our periodic table, fluorine is right here. So it has an electron configuration of 1s2, 2s2, 2p5. That's neutral fluorine. In the problem here, though, we're dealing with a fluoride ion. So this is fluorine that has gained one electron. So if it's gained an electron, we need to add this extra electron to the electron configuration. It's going to be added to this 2p orbitals. And when that happens, then we have 2p6. So the electron configuration for fluoride ion is 1s2, 2s2, 2p6. So answer choice B. Problem 38 says, a period 2 element has the following successive ionization energies in kilojoule per mole. What is the element? If we take a look at the given ionization energy data, it shows a steady increase in energy that's required to remove the first 4 electrons. Then that's followed by a huge energy jump in the 5th ionization energy. This is almost 6 times greater than the 4th ionization energy. So this pattern suggests that the element has 4 valence electrons, and after removing them, the element achieves noble gas-like configuration. So then removing a 5th electron requires a tremendous amount of energy because this is an electron that's coming from a core shell. Since the element is a period 2 element, we need to identify an element with 4 valence electrons in this period. Carbon has a valence electron count of 4. It has an electron configuration of 1s2, 2s2, 2p4 with a total of 4 valence electrons in that second energy level. The first 4 ionization energies correspond to the removal of those 4 valence electrons, and then that 5th ionization energy involves removing a core 1s electron, which obviously requires much more energy. So the correct answer here is B, carbon. Problem 39 says, what is the electron configuration of P3 plus using the noble gas configuration? Our first step would be to write the electron configuration for neutral phosphorus. That is going to be, in noble gas configuration, that's going to be neon, since that is the last noble gas we pass before we make it to phosphorus. After that, we fill in the 3s2 orbital, and then the 3p3 orbital. Now, this is just neutral phosphorus, but what we're dealing with is phosphorus 3+, which means it's lost 3 electrons. We need to remove that from the valence electrons, and specifically since this is a p block element, it's going to lose its p electrons first. We're going to, in fact, lose all 3 of our 3p electrons, meaning that the electron configuration for phosphorus 3+ is neon 3s2. And that best matches answer choice D. Problem 40 says, select which is correctly paired. Answer choice A says that the full electron configuration for calcium 2+ is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now, this is incorrect. Let's take a look at neutral calcium. Neutral calcium is right here, and it has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. For calcium 2+, it's lost 2 electrons, and it's going to lose them in the 4s2 orbital. So this would be the electron configuration for calcium 2+, not this. It would not have any electrons in the 4s orbital. So A is incorrect. B says this is the orbital diagram for silicon 4+. Looking at this really quickly, our eyes should immediately gravitate over here. The diagram does not follow Hund's rule. Hund's rule says that you have to put each individual electron in its own orbital before you ever start pairing them up. So if you were to draw this properly, you would have one electron in this 3p orbital and another one in this 3p orbital, as opposed to pairing them up. So B is incorrect. C says that palladium 2+ has the following electron configuration. This is incorrect. Let's take a look at neutral palladium. That's going to be right here, PD. Its electron configuration is going to be krypton, 5s2, 4d, 1, 2, 3, 4, 5, 6, 7, 8. So this is the electron configuration for just neutral palladium. In the problem, we want the electron configuration for palladium 2+, which means it's lost 2 electrons. For D block elements, you're going to lose your electrons in the higher s orbital first before you touch any of the D electrons. So palladium 2+ would have an electron configuration of krypton 4d8. What they have written here is incorrect. They removed the 2 electrons from the d orbitals first, as opposed to the s orbital here. So C is incorrect. D says the electron configuration for the bromide ion, so bromine -1, the noble gas configuration is just krypton. So let's take a look at this. Here's bromine, all right? If it gained an electron, it would in fact have the same electron configuration as krypton. So this is true. D is the correct answer for problem 40. The next question says, what quantum numbers could be used to describe the highest energy electron in aluminum? Step number 1 is to write the electron configuration for aluminum. Aluminum is right here. So its electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p1. So let's copy that down. 1s2, 2s2, 2p6, 3s2, 3p1. So this problem wants us to figure out which set of quantum numbers could describe the highest energy electron in aluminum. That's going to be the 3p1 electron. Now, 3 tells us our principal quantum number, and the P tells us our L value. When L is equal to 1, we're dealing with the P subshell. This information alone is going to help us easily choose the correct answer because there is only one option where N is equal to 3 and L is equal to 1, and that's answer choice D. So 41 is D. 42 says select the following statements about electrostatic effects that are false. Let's read through each answer choice and figure out which statement is false. A says outer valence electrons shield inner core electrons from the pull of the nucleus. This statement is completely false because shielding occurs primarily when core electrons block the attraction of the nucleus for outer electrons. They have it backwards in this statement. In fact, A is the correct answer for 42, but we're still going to read through B, C, and D. B says splitting of energy levels into different sublevels is affected by orbital shape. This statement is true because different orbitals, S, P, D, F, experience different penetration and shielding effects. And electrons in orbitals with higher angular momentum are less effective at shielding themselves from the nucleus, causing energy levels to split. C says an atom with a higher effective nuclear charge will have a higher ionization energy. And this is true because effective nuclear charge represents how strongly the nucleus attracts valence electrons. A higher effective nuclear charge means that the valence electrons are held more tightly, making them harder to remove and increasing ionization energy. Finally, D says electron repulsions counteract nuclear attraction. And this statement is true because electrons repel each other due to their negative charges. So as more electrons are added to an atom, they increase electron repulsions, which push them further apart, and it reduces the net pull from the nucleus. However, this repulsion is usually weaker than the attraction from protons, which is why the overall structure of the atom remains stable. With that, we move on to problem 43. Problem 43 says, which atom has the highest effective nuclear charge? For this problem, we're going to be using our equation for effective nuclear charge. This equation says that effective nuclear charge is equal to the atomic number minus the number of core electrons. Let's start with boron. Boron is over here on the periodic table. It has an atomic number of 5. So that's our Z value. This means that neutral boron has 5 protons and 5 electrons. Now, from these 5 electrons, we need to figure out how many are valence electrons and how many are core electrons so we can determine our S value. Let's start by writing the electron configuration for boron. It's going to be 1s2, 2s2, 2p1. For p block elements, the number of valence electrons are determined by the highest energy shell, which is going to be n equals 2. So we'll look at 2s and 2p. We'll sum up the 2 and the 1, and that gives us our total number of valence electrons for boron. To figure out the number of core electrons, we're going to take our total number of electrons, 5, and we're going to subtract the number of valence electrons from that, and that value gives us our core electrons. We have 2 core electrons in boron, which means our S value is equal to 2. Now we can plug this into our equation for effective nuclear charge. 5 minus 2 is equal to positive 3. So the effective nuclear charge for boron is plus 3. Now we could do phosphorus next. That's over here. It has an atomic number of 15. So that means a neutral phosphorus atom has 15 protons and 15 electrons. So our Z value for phosphorus is 15. Now, from these 15 electrons, we need to figure out how many of them are valence electrons and how many of them are core electrons. And to do that, we need to write the electron configuration for phosphorus. We can do it using the noble gas notation. So neon, 3s2, 3p3. And for p block elements, the number of valence electrons depends on the highest principal energy level, which is 3. So we consider 3s2 and 3p3, and we add 2 plus 3 to get 5. 5, that's the number of valence electrons in phosphorus. How about the number of core electrons? How do we figure that out? We just take our total number of electrons, 15, and we subtract the number of valence electrons, which is 5. And that tells us we have 10 core electrons in phosphorus. That means S is equal to 10 and Z is equal to 15 for phosphorus. To figure out the effective nuclear charge, that's going to be 15 minus 10, which is equal to plus 5. We're going to do the same thing for chlorine now. Chlorine is over here. Chlorine has an atomic number of 17. That means a neutral chlorine atom has 17 protons and 17 electrons. To figure out the number of core electrons, we need to write the electron configuration first. It's going to be neon, 3s2, 3p5. We sum up 2 and 5 here, and that gives us 7. Chlorine has 7 valence electrons. How many core electrons does it have? To figure that out, we take our total number of electrons and subtract the number of valence electrons. 17 minus 7 is equal to 10. So chlorine has 10 core electrons. This is our S value, and 17 is our Z value. So for chlorine, the effective nuclear charge is going to be 17 minus 10, and that's equal to plus 7. Last but not least, we have lithium, which is over here. It has an atomic number of 3, which means that a neutral lithium has 3 protons and 3 electrons. If we write the electron configuration for lithium, it's going to be 1s2, 2s1. That means 1 electron is the valence electron, and the other 2 are the core electrons, so S is equal to 2. Finally, we can plug it in so we can get the effective nuclear charge. For lithium, the atomic number is 3. The number of core electrons are 2. 3 minus 2 is plus 1. The element with the highest effective nuclear charge is going to be chlorine with a plus 7 value. Now we can move into problem 44. Problem 44 says which atom has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. We really just need to pay attention to this ending right here. So we can go to our periodic table. We're going to do some erasing, and then we're going to try to figure out which element this is referring to. The last few orbitals that are filled are the 4s2 and then the 3d1. So we can go to n equals 4 this period. 4s2 is filled, and then it's just 3d1, which is going to be SC. So the correct answer here is C. Problem 45 says, which atom has the electron configuration? Krypton, 5s2, 4d10, 5p3. Once again, we can go, here's krypton, and then here's our n equals 5, period. All right, we fill our 5s2. Look at that, 5s2 is filled. Then 4d10 is filled, so we make it through the whole 4d block. And then the last orbitals that are filled is the 5p orbitals, 5p3. So that's 1, 2, 3, we land right here. So that is our atom of interest, and that means the correct answer for 45 is B. 46 says, what is the electron configuration for cobalt 3+? To answer question 46, we need to start with writing the electron configuration for neutral cobalt. Let's look at our periodic table. Cobalt is right here. Its atomic number is 27. Let's go ahead and write its electron configuration in the noble gas notation. The last noble gas we pass before we get to cobalt is argon. Then the orbitals we fill are the 4s2 And then 3D, 1, 2, 3, 4, 5, 6, 7. 3D7. So this is for neutral cobalt. However, the problem wants the electron configuration for cobalt 3+. That means cobalt has lost 3 electrons. For D block elements, we're going to lose those electrons first in the highest s orbital, the highest energy s orbital. So 2 of those electrons that we lose out of the 3 are going to come out of the 4s orbital. So we lose those. And then that last and third electron will finally be removed from the d orbitals. We don't want to touch those until we've removed the highest s orbital electrons. That means the electron configuration for cobalt 3+ is argon 3d6. And that matches answer choice A. So 46 is A. 47 says, what has the lowest first ionization energy? Nitrogen, oxygen, fluorine, or neon? Looking at our periodic table, we can find all of those elements in period 2. Here's nitrogen, oxygen, fluorine, and neon. Now, ionization energy, when we discussed it, we said it generally increases from left to right. So you would then assume that based on this trend, nitrogen would have the lowest ionization energy among the given choices. However, this is one of the exceptions we discussed in class, and it arises due to electron configuration and orbital stability. The key to understanding this exception between nitrogen and oxygen is to understand the difference between a half-filled P3 and a partially filled P4 orbitals. Nitrogen has a 2p3 configuration, meaning it has 3 unpaired electrons occupying different p orbitals. And this is relatively stable. This is a stable arrangement due to the minimized electron-electron repulsions. Each electron gets its own orbital. In contrast, oxygen has a 2p4 configuration, meaning it has 1 doubly occupied p orbital. The extra electron in this orbital increases electron-electron repulsions, and it actually makes it slightly easier to remove 1 electron from oxygen than it would be for nitrogen. And so as a result, oxygen has a lower first ionization energy than nitrogen, and it also has a lower ionization energy than fluorine and neon. So the correct answer here is B. 48 says, rank the bonds in order of increasing electronegativity difference. For this problem, we need to recall the electronegativity values for the handful of atoms that we discussed in class. The bonds that we are trying to rank are carbon and nitrogen, carbon and oxygen, boron and fluorine, boron and hydrogen. So let's take a look at our electronegativity table here. For the first bond, the carbon and nitrogen, carbon has an electronegativity value of 2.5, and nitrogen has a value of electronegativity of 3. So we need to take the difference between these two values. 3 minus 2.5, that's equal to 0.5. Then we do the same for this next bond, the carbon to oxygen bond. Carbon has an electronegativity value of 2.5, and oxygen has an electronegativity value of 3.5. So we take the difference, 3.5 minus 2.5, that's equal to 1. Next we have boron and fluorine. Fluorine has an electronegativity value of 4, and boron has an electronegativity value of 2. 4 minus 2 is equal to 2. Then last we have boron and hydrogen. Boron has an electronegativity value of 2. Hydrogen has an electronegativity value of 2.1. 2.1 minus 2 is 0.1. So now we want to rank the bonds in order of increasing difference in electronegativity. So we'll start off with the lowest and go to the highest. The lowest difference in electronegativity is between boron and hydrogen, followed by carbon and nitrogen, followed by carbon and oxygen, and then finally boron and fluorine. So the answer choice that matches that ranking is going to be answer choice B. Now we move on to problem 49. Problem 49 says, as effective nuclear charge increases, ionization energy blank and atomic size blank. As we move across a period in the periodic table, the effective nuclear charge increases because additional protons are added to the nucleus, while electrons are added to the same energy level. This stronger attraction pulls electrons in more tightly, making them harder to remove, and that results in an increase in the ionization energy. At the same time, because the electrons are pulled closer to the nucleus, the atomic size is going to decrease. So in this first blank, ionization energy increases, and in the second blank, atomic size decreases. The correct answer is B. Now we move into our last and final problem. Problem 50 asks, which electron configuration violates the off-bow principle? The off-bow principle states that electrons fill the lowest available energy orbitals first before moving to higher ones. So let's work through the answer choices. A says 1s2, 2s2, 2p6, 3p6. This violates the off-bow principle because it skips the 3s orbital entirely. Normally, electrons should fill the 3s before moving to 3p. And in fact, A is the correct answer for 50, but we're still going to work through B, C, and D. B says 1s2, 2s2, 2p6, 3s6. This violates the Pauli exclusion principle because 3s6 is impossible. Each orbital can only hold 2 electrons with opposite spins. B is incorrect, but it's also not what we're looking for. We're looking for an electron configuration that violates the off-bow principle, hence why the correct answer was A. B is also wrong, but instead, it violates the Pauli exclusion principle. C says 1s2, 2s2, 2p6, 3s2. This is a perfectly acceptable electron configuration. And then D says 1s2, 2s2, 2p6, 3s1. This is also a perfectly acceptable electron configuration. So the answer for problem 50 is A. And with that, we've completed this exam review. I hope it was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.